Hi, in this video I will show you how to check if a set of data follows Weibull distribution, and also more importantly how to plot the confidence band of Weibull plot. Also I will talk a little bit in depth about the concept of median rank, how it is calculated and why it is calculated the way it is. So let us start with Weibull distribution. So this is the probability density function for two parameter Weibull distribution. And this is the cumulative distribution function. We have two parameters, alpha and beta. Alpha is the scale parameter and beta is the shape parameter. Here is an example of probability density function, blue, and cumulative distribution function, red, for alpha equal 10 and beta equal 30. So obviously, cumulative distribution function starts from 0 and eventually it ends up to be 1. If we evaluate this cumulative distribution function at position of alpha at scale parameter. So obviously we put alpha here, alpha with alpha disappears, this is 1. So it's 1 minus e power minus 1, this is 0.63. So at position of alpha, Weibull cumulative distribution function is equal to 0.63%. Now imagine if you have a set of data, we want to see whether this set of data follows Weibull distribution or not. What we have to do? First, we have to study a little bit of mathematics. This is the cumulative distribution function. We rearrange it. We write it like this. Take the logarithm. It becomes like this. Multiply 2 minus. Take another logarithm. Then you end up to have this equation. Now assume that this is y. This ln x is x prime. And this one is a. What do we get? Y is equal beta times x prime plus a. So this is the equation of a line. So this means if we take the log of the data, we put the log of the data in the x-axis. And for the y-axis, we calculate this parameter, log of minus log 1 minus fx. If the data follows Weibull distribution, that would be a line. So all the data will sit around a line. And we can actually evaluate the parameter of the line. We can calculate its slopes and its intersection with the y-axis. So we can actually get beta and a. If we have beta and a, we can also calculate alpha. So as soon as we have the line, we can get the parameter of the line. And from there, we have alpha and beta parameter of the Weibull distribution. Now, the question is how to make this graph and how to make the confidence band. Notice that the only parameters that you have, the only data that you have is basically your measurement data. For example, is time to breakdown, is breakdown voltage, whatever that is. So you have this information that, let's say the sample broke after 100 hours. The second sample broke after 300 hours and so on. We do not know exactly each of these samples, how it is correlated with probability of failure. So we need to do some kind of estimation. So we have to estimate the probability of failure for each of those samples. Because we do this estimation, the line that we obtain here, it will not be 100% certain. So this line can actually deviate. And because we want to know how much this line will deviate, we are going to plot the confidence band. So for example, 5%, 95% confidence band, then we say that, okay, this line maybe can be a little bit different, but at least we know the range of it. So this is what we are going to study. All right, so now assume that you have a set of data and you want to make the Weibull probability plot. So this data that I have, they are breakdown electric field for certain samples. So this is 60.89 kilowatt per millimeter. Second one was 56.06 and so on. First thing that you have to do is to sort the data in ascending order. And the second step is that we want to estimate the probability of failure corresponded to each of these data. Now, there are many equations that they evaluate the probability of failure, or what we call it median rank. For example, we can use beta distribution. The beta distribution will give you the exact prediction of median rank, which we have to evaluate this formula. Or there are many approximate formulas that we can use. For example, this formula is rather simple. You can just put I. So this is sample number 1, this is sample number 2, and then you can get the median rank corresponded to that sample. For example, this is another formula. MATLAB uses this formula for Weibull probability plot. Okay, so now we will see why we use these formulas and where they come from. Now, it's obvious that if you have these formulas, you can evaluate the probability of failure for each sample, and then we can actually create this plot because we have the x-axis and we have the y-axis. We sort it in this format, and then we make the plot. Okay, at first glance, when you look at these problems, you say that I have, for example, in this case, I have 11 samples. So obviously I have to assign the first one 1 over 11, maybe the second one 2 over 11, and so on. So why don't we use this estimator to estimate probability of failure for each sample? The problem is that you take, for example, 11 sample from a million product, and it happened that they are, let's say, like this, randomly distributed on the main distribution function. Now, if we assign this one 1 over 11, this one 2 over 11, and so on, the last one will become 11 over 11. So the last one, we have to assign it as full 100% failure probability. However, if you would have selected a different set of samples, so 11 sample randomly you select again, in that case, you notice that there are many samples that can happen actually after this sample that was here. So if I assign the probability of failure here to 100%, then actually I am ignoring all these points that may happen after this. So therefore, using this estimator for calculating median rank is not a wise thing. Same way, we cannot use I minus 1 divided by n, because in this case, we will have problem for the first sample. These type of estimators, they call it naive estimators, so they're not very accurate, especially if the number of samples are few, they will not be very accurate. If the number of samples are huge, then these estimators and the other estimators, they give very similar results. Okay, so now if I have a set of data like this, how should I decide what value of probability of failure I should assign to this point, what value should I assign to this point, and so on? What is the best strategy? Here I'm going to use a MATLAB code to visualize this problem a little bit better so that it sticks to your brain forever. Let's have a look. All right, now let us assume that we have a product that 100% follows Weibull distribution. And I'm going to select 11 samples from this product. Obviously, because it follows Weibull distribution, all the samples are on cumulative distribution function. I've marked the first sample with red and the last sample with green. Here we can easily read the probability of failure for the first sample, the probability of failure for the second sample, and so on. But in reality, obviously, we don't have this distribution. We only have the data point. And we want to assign the probability of failure to each of these data points. So how we are going to do that? Let me I delete the data points, only I keep the first data point and the last data point. We can do for any other points, but for illustration, I will just keep these 2 points. Now let us take another random 11 data from this distribution. Okay, if we take another random 11 data, it's like this. So this is the first one, this is the last one. I can delete the rest of the data. You notice that the first point, it happened here again. This last point happened there. Okay, that is interesting. Let us repeat this procedure many times, 200 times. If we repeat this procedure many times, what you notice is that the first sample is very likely to happen in this region, where the second sample will be most likely happen in this region, and so on. The last sample will happen here. Now, the first sample, it can also happen at this region, at this point, for example, but it's very unlikely. Because if the first sample happened here, it means all the other samples should be within this region. And if you look at the probability density function, that means if the first sample is here, that means we are on this location of probability density function. And since all the other samples happen after the first sample, everyone should be from this region, which is very unlikely that all the samples happen there. But if we repeat this process millions of times, billions of times, we will probably see some samples that the first sample is located here. But anyway, most of them are located here, and for last sample, most of them are located there. Now, when we have 11 random data, we don't know where the first point is. From this distribution that we have, we don't know where the first point is. Maybe it's here, maybe it's here. We don't know where the last point is. Maybe it's here, maybe it's there. So if I want to assign a probability of failure to the first point, the most logical thing that I can do is to consider this distribution, calculate the median of this distribution, and assign this median to my first sample. So that's why we call it median rank. So we calculate the median of this, and that probability will be assigned for the first sample. We calculate the median of the second distribution and assign that to the second sample, and so on for the last data point. So we calculate the median of this and assign it to the last data point. If we want to calculate, for example, 5% confidence band. So with 5%, instead of calculating the median, we calculate the 5%. So with 5% chance, basically everything will be here. With 95%, we come to somewhere here. And basically we calculate probability of failure for 5% and probability of failure for 95%. And we assign that one to the first sample. Same way we do for all samples. And from there, we can calculate the confidence band of 5% or the confidence band of 95%. Now that we understood the concept, I will tell you how to calculate the median from this distribution. How to calculate the median from this distribution. So in order to calculate the median rank very accurately, we have to use this formula. This is the exact formula. If you want to find, for example, median rank, then this P is 50%, so 0.5. And basically, we have to solve this equation multiple times. For example, if you want to find median rank for sample 1, you put J1, and then you calculate the summation, and you solve basically this polynomial. There will be a summation of polynomials equal to 0.5. And when you solve it, you get the median rank for the first sample. And if you want to find median rank for the second sample, you put J2. Again, you sum them equal to 50%, and you solve it, you get median rank for the second sample. Now, this formula, I spent many hours to find somewhere on internet that explains how this formula came into existence, but I did not manage to find that. Eventually, I decided to use my own brain power and show where this equation comes from. So I will show it to you at the end of the presentation. Now, using this formula is a little bit complicated because you notice that there are many polynomials that are multiplied together and then add together and then should be equal to 0.5. So it's not very straightforward to calculate this median rank. So many people, they came up over the time and they proposed some equation to calculate median rank. Most of these equations follow this pattern, I minus c divided by n plus 1 minus 2c. C is something between 0 and 1. So for example, Weibull proposed I divided by n plus 1, Hazen I minus 0.5 divided by n. And this is what is used in MATLAB. And this is another one which is very accurate if you compare it with the exact one. And this is another one. Okay, so these are all estimators. They are approximate. This is the exact formula. We can also obtain the exact median rank using beta distribution. This is something that I'm going to show you here. Now, the information in this page is from the book of our professor, Professor Rob Rose, Reliability Analysis for Asset Management of Electric Power Grid, page 108. If you want to read more, you get this book. Okay, so let us assume that we have n samples, and we want to calculate the cumulative distribution function for sample I. In order to do that, first we calculate probability density function of sample I. Also, let us assume that for each individual sample, the chance of failure is P. In order for sample I to fail, we must have first I minus 1 sample that they have failed already. So the probability of this is p power I minus 1. And the rest sample n minus I, they should not have failed. So that is 1 minus p power n minus I. Now totally we have n samples, so we have n factorial combinations. And within this category, we have I minus 1 permutation, so I minus 1 factorial. This is only one unit, so this is 1 factorial. This is n minus I item, so we have this many permutations, so we have to divide them. So probability density function for sample I is actually something like this. So if you want to find the cumulative distribution function, the d, basically the small part of it, is probability density function times dp. We have it like this. Instead of these factorials, we can use gamma function here. And now we can integrate the d, f, I, and n from 0 to whatever percentage that we want. So from 0 to f, I, and n, and p. So this gives us the p% of the probability of failure. And on the other side, we have these coefficients integration from 0 to f, I, and n, and p. Now this integration is actually beta distribution. So you can see here beta distribution for variable x and parameters alpha and beta. So this is exactly beta distribution. Beta distribution for parameter I and n plus 1 minus I. So I, n plus 1 minus I. So if you want to have a probability of failure, whatever that is, maybe 50%, 5%, 95%, that one should be equated to beta distribution of cumulative distribution function of sample I and n with p%, and parameter of beta is I and n plus 1 minus I. Okay. So this cumulative distribution function of sample I basically follows beta distribution. So if you want 8% probability of failure, we can calculate this beta distribution. Or if we want to find this probability of failure, we can take the inverse of beta distribution with 8% I and n plus 1 minus I. For example, to find the median rank, that is the 50% probability of failure, we take the inverse of beta distribution 0.5 I and n plus 1 minus I. If you want 5%, here we put 5%. If you want 95%, we put 95%. So based on these equations, we can actually use MATLAB to evaluate the median rank, or to evaluate 5% confidence or 95% confidence band. And then we have the estimation for probability of failure, whether for 50%, 5%, or 95%. And also we have the data. We can plot the Weibull distribution and its confidence band. So this is what I'm going to show you in MATLAB. And after this, I will show you how to prove that equation. Basically, that equation is equal to the beta distribution. And I will demonstrate this at the end. It's too much mathematics, not very interesting for many people. All right, so now let us see how to plot Weibull distribution over a set of data. So here I have a set of data. These are breakdown strength of some insulation material. Basically, MATLAB has a function, Weibull plot, your data set, and that produces Weibull plot. Also, you can calculate the parameter of that Weibull plot using the function Weibull fit. Let us see how to do it. If I run this piece of code, basically you notice that we have the Weibull fit. This axis is the data, and this axis is probability of failure. Now, how MATLAB makes this graph? Basically, you have the data. MATLAB assigns the median rank. We will discuss it. And after that, basically, it creates this plot. It connects the first quartile of the data to the third quartile of the data. That creates the solid line. And then it extends the solid line that creates the dashed line. The first quartile means that, for example, if we have 100 data, it takes data number 25 and connect it to third quartile. That means data number 75. And that basically forms the line. And then it extends it. Using the slope of line and y intersection, basically it can calculate the parameter of the line as I showed here. So if I take this Weibull plot and we use it in MATLAB, so you notice that here it gives you the scale parameter and also the shape parameter. If we use A and B Weibull fit, A becomes the parameters of this line, a scale and shape parameter, and B will be 5% and 95% confidence band for the parameters for a scale and shape. Okay, so this is what MATLAB does. Now let us see how this information is plotted. We have the set of data. As I mentioned before, MATLAB uses a median rank of I minus half divided by n. So we have the set of data, we sort it. In that function itself, it will sort it. Here we sort it manually, and then we calculated the median rank based on this function. And now we are going to plot. So we're going to plot data versus log of minus log of 1 minus fx. Okay. Now you notice that here I'm plotting the data directly versus this. In this analysis, we said that we plot log of data versus this. Then it becomes a line. Here I'm going to plot the actual data versus that. If I do this, you notice that what we produce exactly fits to what MATLAB has produced. So this is basically the way to do it. Now the reason that I put here the actual data, not log of the data, because this axis itself is logarithmic. So therefore, we don't need to put another logarithm here. Now, when you want to find the slope of the line, you must take the logarithm. So you take the values, for example, here is 34, and this is, for example, 26. You take the logarithm of 34 minus logarithm of 26 and divide it by the parameter that is in the y-axis. Okay, so this is what basically MATLAB does. If we use other estimators, for example, if I use beta distribution, the exact estimator, and if I do the same thing, you notice that the data points will be slightly different places. So instead of being here, this is what MATLAB produced, but we estimated to be here. Or instead of being these, it will be somewhere a little bit different. And if we use other estimators, this estimator, I said that this is more accurate. This is more close to the beta function. So if I run this estimator, you notice that it's more close to what beta distribution predicted. Okay, let me delete this and I plot it again. So here is the plot by MATLAB. What we can do is that we can now calculate and plot those confidence bounds. So the procedure is that, let me zoom in. Again, we sort the data. In this case, we calculate 5% confidence. We calculate the beta inverse of 5% on this one to get the ranks. And in order to plot the confidence band, so we calculate this 5% band and then we feed it back to the Weibull distribution using the scale and shape parameter that we calculated before. So basically we have this equation, we multiply it to a minus and we take power 1 over beta, so this beta disappear, multiply to alpha. In that case, we can have basically the value of data, we can obtain it like this. And now we can plot the data versus the probability of failure that we have estimated. So if we do this, basically, this would be 5% confidence band. And here, if we do this, this will be 95% confidence band. You notice that here is the data, and for 5%, the data can even go down to these numbers, and for 95%, it can go up to these numbers. And same for each probability of failure, we can find how far the data can go if the actual probability distribution is this function, is this line. So this is basically how to plot the confidence bound directly in MATLAB. What we could do also is that we can calculate also the line ourselves. So here we have the MATLAB plot. What I'm going to do using these commands, I'm going to delete every information that is within this graph because I want to keep the axis. The axis is already constructed for us in a nice way. So we keep the axis and then we put the data on this plot using the beta distribution. So we sort the data, we estimate 50% rank, basically median rank, and then we plot it. Okay, that is the data. And now we want to find the line that fits to this data. But in this case, I'm not going to use the method that MATLAB used to connect the first quartile to the third quartile. I'm going to use least square fit. So this is done here. I zoom in on this. First, we sort the data. Sometimes the data has a duplicate, and later on we are going to use a fit. MATLAB does not accept duplicate when you want to use the fit function. So with this piece of code, basically what I do is that whenever there is two items are equal, I just increase one of them very tiny amount. It doesn't change the plots, but it avoids to have duplicate. Basically with this, we have a set of data that is sorted and they are not duplicate. And same way as before, we estimate the rank, 50% rank. We are going to fit a line to this data. So here we need really to use the log of the data versus log of minus log of 1 minus fx. So we are going to fit a polynomial of one order, basically a line to this data. So that forms our line. So this p has two coefficients. One of them is the slope, one of them is y cross section. So basically P1 and P2. And now we can plot the polynomial. So we plot the x versus log x multiplied to the slope plus the constant. Again, here you notice that, let me zoom out. Here you notice that we should plot this x prime is log of x multiply beta plus a. But then I plot only the data because the axis itself is logarithmic. So data versus log of data multiply P1 plus P2. And also using the same equation. So for example, P1 is beta and this A is P2. We can also calculate alpha. That is done here. Basically beta is P1, alpha is this one. And yeah, we have the line which we can plot it. This line is the fit with least square fit, basically. It's a little bit different than what MATLAB does. And now here also what I have is the comparison between what MATLAB obtained with what we obtained using least square fit. You notice that this is the scale parameter and shape parameter obtained by MATLAB, and this is a scale parameter and shape parameter obtained by us. Okay, so we have this information, and then basically we can use this information and also add the confidence bond using the previous strategy, as I said. Now, because the scale and shape parameter for MATLAB was very similar, so I'm going to use the same thing in plotting confidence bond. So this is 5%, and this one is 95% confidence bond. So we can use this one, we can use this one. So if you wanted to use correct parameter that you estimated for this line, instead of, for example, instead of this term, which is the scale obtained by MATLAB, we have to use our own scale. And here, instead of this parameter, we have to use our own shape, the one that we obtained. All right, by now you already understand how to plot the confidence bound and Weibull plot, basically in MATLAB. I can put this code somewhere, maybe in the description, so that you can use it. The last part of the video is that I'm going to show you how to obtain this formula, basically. So I showed you about the cumulative distribution function of sample I, and this was this equation after we took the integral from 0 to fi and n x%. Basically, the integral goes there, and this one is equal to whatever percentage that we want, becomes equal to this equation. So p here, we showed that is equal to this integral multiplied to this coefficient. But at the same time, I said that p is equal to this equation. If you want to calculate median rank, we can also use this equation. So this is exact equation. How come that these two equations are the same? That is what I'm going to show you now. Let us evaluate this integral. We are going to use integration by part. So integral v du is vu minus integral u dv. So in this case, we consider v is 1 minus p power n minus I. So this part, dv becomes this. And du is p power I minus 1 dp. And we take the integral, u becomes p power I divided by I. Okay, so this whole integral will be this constant multiply vu is this one, multiply this, and then we have to evaluate it from 0 to z, plus integral from 0 to z, actually u dv. So this is u and this is dv. Here it becomes plus, here is minus, but because we have another minus here, so this becomes plus. Now after you evaluate this one, this becomes z power I multiply 1 minus z power n minus I. And this I will also come here. It creates I factorial. So this whole is basically selection of I item from n item. And this is the resting that we have. So after simplification, basically you notice that after running one time of integration by part, we get I from n, z power I, 1 minus z n minus I, plus this whole term. We can do the same procedure again, integration by part. And in this case, what happens is that this term will come out. Basically, I plus 1 from n item times z I plus 1 times 1 minus z n minus I minus 1. You can repeat this procedure. So these items will be obtained. And eventually, we get to the last term because the power of this 1 minus p becomes 0. So this one, then we don't need to do integration by part. We can just directly integrate it. And that integration becomes z power n divided by n, basically. This should not be, there's some mistakes here. This should be, yeah, I think there's some mistake here, a little bit of mistake. This should be minus 1. This is correct. Okay, so after taking the integral, this becomes z power n divided by n. So this one with this disappears, so this is 1. But instead of writing 1, we can write n out of n, z power n. Now this summation is actually exactly this summation. So that's why the beta distribution, which we calculated before, basically this one is equal to p, and also this summation is equal to p. So these two actually they are identical. Now you know how to derive this formula to calculate the exact value of median rank. Of course, you can use this formula or beta distribution. All right, so this is end of the video. I hope that the information is useful for some of you. And now you know exactly how to plot Weibull distribution and its confidence band in MATLAB. See you next time. Bye.